Hello, welcome back to CS700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. Last time we have analyzed the computational cost of several algorithms for common numerical problems. Problems like differentiation, which is an operator, turned out to map polynomial time computable functions to polynomial time computable functions. Its converse integration, however, did not seem to map polynomial time computable functions to polynomial time computable functions. We were able to show that integration is possible in exponential time, actually in polynomial space, and we could show with a device and analyzed algorithm that performs indefinite integration in polynomial time, provided that fp function in polynomial time is equal to sharp p, this large complexity class that is includes even more complicated problems than NP. So let us briefly recall these problems and their algorithms and their analysis, then proceed to what is really one of the highlights of this entire course, namely proving that our complexity analysis and the algorithms are optimal. And this is really something that only computer science provides the techniques to establish such rigorous proofs of optimality. And the new thing is that this is now for problems from numerics involving continuous data. Okay, so let me show you the slides. Here we are. Yes, so the first problem we considered was parametric maximization, maximizing a given function, computing the maximum of a given function up to a certain argument x. And with this argument varying, the result of this maximization is again a function. Therefore, maximization is an operator. And we showed that rigorous algorithms can compute that parametric maximum in polynomial space, but that this can be even improved to polynomial time, provided that the millennium problem P versus NP has a positive answer. And the proof of that uses some certain problem that we've constructed on the way, a decision problem, which turned out to belong to this class NP. And by repeatedly invoking an algorithm that solves this problem in polynomial time based on the hypothesis that P is equal to NP, we were able to devise an algorithm that determines the maximum of the function using bisection. So repeatedly using that problem, invoking the algorithm for that problem. So this was in several ways not at all a classical NP completeness proof. First, because NP completeness, the underlying concept of polynomial time reduction, inherently is tailored for decision problems. But here, of course, this is not a decision problem. This is not even a classical function problem. This is a continuous function problem. The next operator we considered was the indefinite integration, where we could similarly show that, well, it can be done in polynomial space too, and it can be improved to polynomial time, but now under a stronger hypothesis. The stronger hypothesis being that fp is equal to sharp P, this complicated complexity class. And again, for the proof, we would construct a certain integer counting problem, maybe a problem that we could show to belong to this class sharp P, and using the hypothetical algorithm that solves this counting problem in polynomial time would allow us to compute the indefinite integral in polynomial time. And a subtle difference to the algorithm and proof and analysis from the previous slide, let me point out that here this discrete problem is invoked only once. So this is kind of getting a little bit closer to the idea of a polynomial time many one reduction, whereas the example in the previous slide where we would invoke that several times, this is more like Turing reduction, where we can invoke a problem several times. So, but later we will formalize different notions of reduction for continuous problem, generalize polynomial time reduction from discrete decision problems to continuous problems based on the PhD thesis of Akitoshi Kawamura. Okay, next we had considered definite integration, where the upper and lower integration bound are fixed, 0, 1, for instance. And then we could show that the complexity boils down to sharp P1 to the unary complexity class. Well, that's not entirely true. Let me be more specific. The hypothesis was a different one. So for indefinite Riemann integration, the hypothesis was that fp is equal to sharp P. Polynomial time computable integer functions are the same that can be counted, polynomial countable integer functions, counting the number of witnesses. Here, the hypothesis is that the unary versions of both complexity classes coincide, and it's not clear how these two conjectures are really related to each other. There's many open questions about the conjectures and about the relation between conjectures. So intuitively, the problem should not get more difficult when fixing the upper integration bound when proceeding from indefinite to definite Riemann integration. And then finally, we considered the problem of solving ordinary differential equations, which is a more general problem. It includes the problem of antiderivative of indefinite integration. And then we had to be a little bit more careful about the hypothesis. Indefinite integration, Riemann integration, is mathematically well defined for every continuous function. And we know that if the function under consideration is fixed and computable, a polynomial term computable, then it is continuous and therefore has an antiderivative. Whereas when we consider solving ordinary differential equation, there's these infamous counterexamples where the solution exists, that's asserted, but not unique. And there are many solutions in general. And the complicated counterexample shows that in general, none of these solutions may be computable. It's an artificial one, but it demonstrates the limitations. So here we had to strengthen the hypothesis in order to assert uniqueness, and uniqueness that's in many cases in computable analysis, uniqueness of a solution also exerts computability by some fundamental principle. And here to this end, we strengthen the hypothesis to the right-hand side to be polynomial time computable, and in addition, Lipschitz continuous, which is not something that follows from the hypothesis directly. And then the solution is mathematically known to be unique. And furthermore, there are common methods, Euler's method, and its generalization Runge-Kutta methods. And our analysis showed that these methods all use polynomial space. We need to make the step width roughly 2 to the polynomial in the output precision parameter in order to ensure that both the errors made in each step and their accumulation, their propagation of the error throughout exponentially many steps still remains bounded by 2 to the minus n. And well, the running time with exponentially small step width is exponential time, but that was also the true for the previous problems. But like the previous problems, one can improve that to polynomial space by reusing basically the memory storing the approximate value of the solution at the current time step and repeatedly invoking, of course, the algorithm computing the right-hand side f, so that overall this is a PSPACE algorithm. So to summarize, in a certain sense, function parametric maximization belong to this complexity class in a certain sense. Riemann integration belong to this complexity class, indefinite, definite to the univary version, and solving ordinary differential equations belong to this complexity class, which is even larger. So we have really a hierarchy of numerical problems that we could locate in this hierarchy, complexity hierarchy. And let me also point out that numerical folklore says that integration should be easier than maximization in the continuous realm, but our complexity analysis suggests differently. But of course, these were only upper bounds. We have designed and analyzed algorithms for these numerical problems rigorously. And what we're going to see today is that our analyses are actually optimal. Okay, and we're going to establish that not using our standard reduction, but by encoding, in a certain sense, decision problems into the continuous setting. So the first we're going to show is that maximization is NP hard. And please notice again the quotes here, because NP hardness, polynomial time reduction, as I keep emphasizing, is not defined for the continuous realm. So let me first state this, the statement to clarify the possible confusion. Namely, the statement says to every decision problem in NP, there exists a polynomial time function. So this is the function for which we're going to compute the parametric maximum. This function is called G. The function will depend on L, so it has a index L. And we're actually going to construct a function with this smooth, but let's ignore that for a moment. Such a function such that the following holds: the parametric maximum of that function, the maximum of that function, or that should be a G, the maximum of that function up to x, if that is polynomial time computable, then actually the original decision problem was already polynomial time decidable. Put differently, from an algorithm which computes the parametric maximum of that function, one can recover a different algorithm that decides the original decision problem in polynomial time. Okay, and you see that how this statement formalizes that maximum is NP hard. I mean, if it's possible to compute the parametric maximum of that function in polynomial time, then actually the two classes P and NP collapse and coincide. But the statement does not involve any reduction, any polynomial reduction. And also let me emphasize that the function we're going to construct, well, to be fair, it's going to be an artificial function, but then again, define what is an non-artificial function. That's not a mathematical statement. And the function the way we construct it, it's going to be a smooth function. So again, as opposed to common belief in numerics, smoothness does not help. Well, it does help, to be fair, but not enough to kind of bridge to cover from exponential time, from polynomial space, from NP to P. Okay, so the acceleration that is feasible due to smoothness remains within the polynomial bound and cannot cover from exponential to polynomial time. Okay, and here's the construction, and the construction is very involved. So this slide has a lot of animations that guide us gradually towards the construction of this function through various intermediate stages. And the basic principle construction brick is this pulse function, smooth function, the infinity function with compact support. So the function vanishes outside of the interval from -1 to +1 identically. In particular, this function cannot be analytic, otherwise its power series expansion here would be the zero function, but it's obviously not the zero function. And as you may recall, this was one of our examples of a polynomial time computable function. So this is polynomial time computable. And here's the kind of explicit expression for that function. So, and we're going to combine shifted and scaled copies of this function, infinitely many, into to construct this function GL here. To this end, we take the unit interval, the domain of the function GL, and subdivide it into smaller and smaller subintervals like this here. We're going to place the first copy of this pulse here and further copies at the positions. So 1, 1/2, 1/3, 1/4, and so on. So harmonic series. So the first corresponds to input 1, input 2, input 3, input 4, and so on. And the scaling of these pulses is designed in such a way that the resulting function is actually still continuous even at 0. 0 is the crucial point here, right? So because the width and the height decrease to 0, yeah, the important thing is the height decrease to 0. Therefore, this function is continuous here anyway, that's no problem, but also continuous at 0. Now the next thing is how the width and height ratio evolves, because as you can see, for example, the first derivative here is has some value, but here it's more steep, and here maybe even more steep. So that means that the first derivative of this final function, may be unbounded at 0. This is not what we want. We want the resulting function to be smooth, including 0. So that also means that the first and second and third and all further derivatives must also tend to 0, right? Not just the value, but also the slopes. And to this end, the following scaling turns out to be sufficient. So we scale the pulses with 2 to the natural logarithm of 1/n. So as you see, as 1/t, as t converges to 0, 1/t converges to infinity. The logarithm of that converges to infinity, but the base of this exponential power converges to 0 faster, so that in the end, indeed, we have this inclusion, this hull that you can easily see to converge to 0. And I'll leave it to you to verify that also all derivatives tend to 0. Well, with different rate of convergence. So first derivative tends to zero faster than the second, then the third, and so on. But this has been carefully designed so that all derivatives tend to zero, and that in fact the resulting function is smooth at including at zero. And now we're going to, so what you see here is a kind of explicit expression for this collection of pulses. So here you see the pulses, they are shifted, right? So you see minus 2 times n, that means a shift, and they're scaled in x direction a little bit stronger, right? So here you see scaling with n squared, n ranging over all natural numbers. So that means the pulses become more thin, but in y direction, they are scaled even stronger, right? So this is scaling stronger than n squared, scaling stronger than n cubed, stronger than n to the fourth, because the exponent here is unbounded. It's a natural logarithm. And this is just barely the threshold that is feasible. So to make sure that also all derivatives of this function eventually converge to zero. And if you take the first derivative, you see that there's an n squared according to the chain rule coming here. Second derivative, there's n to the fourth, and so on. And all derivatives must still tend to zero. And this is what it is achieved by this. Of course, n to the fourth is eventually dominated by the logarithm of n, and therefore tends to zero. So this is an explicit kind of expression, well, as explicit as it can get, because it's an infinite series. And also let me emphasize that the infinite series here, actually, there's nothing to worry about convergence. Well, it does converge, but we wouldn't even need to worry because the domains are disjoint. That's how the scaling and shifting has been carefully designed, such that the domains, the supports of each pulse are disjoint, and therefore at every argument t, at most one pulse is even contributing non-zero to this infinite series. Okay, now that's our first step towards the construction, but of course this does not depend on the decision problem L at hand. So let's, this is a C infinity function. And let's now start and introduce some arbitrary subset of natural numbers. Let's call it V. This will later be the verifier in our NP problem L. And restrict the sum here not to range over all natural numbers n, but only over those that belong to this verifier V. So what does that mean? It means previously we had all these pulses, one for every natural number, but now some of these pulses will vanish and only those pulses remain that correspond to indices capital N that belong to V, right? So only when N is an element of V, the pulse corresponding to this position N will remain and other pulses may be absent. So here's an example. Of course, different choices of capital V lead to different pictures here. Okay. Now let's analyze this resulting function. This resulting function is still in C infinity, right? So all the scaling issues are still in effect. So it's still a C infinity function. Let's now look at the computability and complexity, right? I should first point out that the original function without, where all pulses were present, is actually a polynomial time computable function. This is an important observation. Polynomial time computable, how can we compute that in polynomial time? Well, the argument is t, right? And our algorithm can look in which of these intervals t lies, right? So technically we need to use this join operation at the shared interval bounds, but the main part is we can check in which subinterval t lies and then invoke the corresponding the scaling and invoke the algorithm computing the thus scaled pulse function, which is a polynomial time algorithm. So one subroutine computes this pulse function, and our algorithm just needs to determine how to scale the pulse that is present at the current position. And this can be done in polynomial time. But now that we restrict and only have some pulses present, um, the resulting function may not be polynomial time computable anymore. Actually, what we're now going to demonstrate in our second step of the construction is that this function, which we've constructed just now, depending on the decision problem B, this is polynomial time computable if and only if the original decision problem was polynomial time decidable. Okay, so that's an interesting thing, coding technique, right? So we have, I will explain it in a minute, but this statement says that we have encoded a discrete decision problem into a continuous function in such a way that the complexity of both basically coincide. So this can regard this as an example of our continuous version of a reduction. We have reduced this discrete decision problem to the computation of a continuous function. Well, except there's no notion of reduction, but instead we have this equivalence. So let me explain this equivalence to you. So the first direction is suppose that decision problem B is polynomial time decidable. Then we can compute the function in polynomial time as follows. Again, the same general idea. Given the argument t, determine in which of these subintervals t lies, right? And then check whether this subintervals, the index capital N corresponding to that subinterval, belongs to P or does not belong to P. Okay? And by hypothesis, this can be decided in polynomial time. If it does belong to P, then invoke the subroutine computing the pulse, appropriately scaled and shifted. If the index does not belong to V, then just output 0 because there's no pulse to output, right? So that establishes one direction and observe that indeed the hypothesis that the problem V is polynomial time decidable has entered crucial into our algorithm, right? Now let's look at the converse implication. Suppose that the function is polynomial time computable, then we can obtain an algorithm that decides this discrete decision problem V. In what way? Well, given some integer capital N, check whether this integer belongs to V or not in the following way. Determine the subinterval, the center actually of the subinterval, which corresponds to the input N, right? Here, this center, here, this center, here, this center, and evaluate the function fv at this argument, which by hypothesis is possible in polynomial time, in time polynomial in the output position parameter. And by evaluating this, if the pulse is present, then the value of the function is positive. If the pulse is absent, then the value of the function is 0. Well, but we cannot test for 0 or non-zero, right? So what's the solution to this problem? Well, we don't have to detect exactly whether 0 or non-zero because the pulse, if it's present, has a considerable height, right? Namely the height n divide n to the logarithm of n. So the binary precision in order to distinguish whether pulse is present or not is roughly the logarithm, right? That's our precision parameter. It's always 2 to the something, and we can express that as n to the logarithm of n is basically 2 to the logarithm squared, which is basically 2 to the n squared. So that's quadratic complexity, and in particular polynomial complexity, um, to distinguish whether pulse is present or not by approximately evaluating the function. We only need to evaluate the function approximately up to error 2 to the minus n squared. That's the point. 2 to the minus logarithm capital N squared, which since the logarithm corresponds to the binary precision parameter, is 2 to the minus n squared. So, and then, yeah, thus by approximately evaluating the function, we can detect whether pulse is present or not, and thus recover whether the input capital N belongs to the set V or not. Okay, that was our second phase of the construction of this function. And now we're going to move to the third phase, where we encode an NP problem. So here we have encoded a P problem, right? And now we consider an NP problem. And remember, a prototype of our NP problem is here now with integer input of the following form: the set of all natural numbers n, such that there exists a witness, which we here call capital M, and the witness must have size polynomially bounded in the length of the input, and it is no loss of generality, as you may recall from our complexity recap section, that the witness actually be bounded in value by the input n. So this is what happens here. We've strengthened polynomial in the length of n to value bounded by the value of n. And then check whether the tuple combine both into one single natural number using the Hilbert hotel pairing function. Check whether this tuple belongs to the witness decision problem or not, which is a polynomial time decidable problem. So this is our prototype NP problem, and it's no loss of generality to consider such a problem. And now we're going to encode this problem, discrete problem, into a C infinity function, into a continuous object, but now taking into account both n and m, right? So our witness set here now consists of pairs, whereas the construction we made in step 2 only involves single natural numbers. But the modification is not too hard. Namely, we're going to subdivide each interval here further, right? So we had these intervals, one for each possible input n, and now for each possible input n, we can create a subdivision that also makes room for the possible witnesses. So here, when n is 1, there's there's only one possible witness, namely 0. So we don't need to subdivide here. But here there are two possible witnesses, 0 and 1, capital M can be 0, 1. So here we need to subdivide into 2 parts. Here we need to subdivide into 3 parts, 4 parts, 5 parts, and so on. And this is what you see here, right? So there's a subdivision. The small ticks indicate the subdivision for the witnesses, candidate witnesses, and the large ticks still apply to our original arguments, capital N. So here we have only one possible witness, here we have 2, here we have 3, here we have 4, and so on. And again, we're going to put pulses here, but now the pulses have all the same height, the pulses that correspond to different witnesses for the same input, right? So here, 2 possible witnesses, 2 pulses. Here, 3 possible witnesses, 3 pulses, 4 pulses, 5 pulses, and so on. And again, by our careful scaling, we make sure that this function is still continuous at 0. First derivative is continuous at 0, second, and so on. And to this end, we need to actually make a little bit more room for our new pulses for our new witnesses. So previously the scaling in x direction to make room for these pulses was like here n squared, and now it's n cubed. So it's a little bit tighter scaling, but still everything works out smoothly, literally, because here the first derivative gives an n cubed here, which is dominated by n to the logarithm n, this attenuation here, right? For n large enough, and similarly the higher derivatives n to the 6th, n to the 9th, will all eventually be squished by this scaling in y direction. So this is still, the message is still, this is still a C infinity function with all the pulses. So that's the third step of our construction. Now for the fourth step, we're going to apply the same trick as previously. We're going to remove some of these pulses. Namely, we're going to keep only those pulses corresponding to pairs, right? So now every pulse corresponds to a pair, n comma n. N says which major pulse we're, or major interval we're looking at, and m says which sub pulse at this in this major interval we're looking at. And we're going to keep only those pulses that correspond to such pairs that belong to the set V, basically like the same way we did previously, but now V is this particular polynomial time decidable set, namely the witness set here, verifier set. Okay, so as you see in this example, now again some pulses remain and others have vanished. And let us record. So this new function is still smooth, is still C infinity, and this new function is still polynomial time decidable because, well, for the same reason as previously, now adjusted to the tighter scaling, namely we can evaluate the function by checking now which pair n comma m the given argument t belongs to, which subinterval indexed by n comma n t lies in, and then invoking the decision procedure to see whether this subinterval belongs to B or not. And if it does, invoke the subroutine that calculates the appropriately scaled pulse and otherwise just outputs 0. So the basic message is this is a polynomial time computable smooth function. And actually, this is our resulting function. This is the function we're going to use. This is the function that occurs in the theorem. This is going to be our GL. So we're almost there, right? The first, the fourth step, we have constructed this function. Now let's look at the parametric maximum of this function on the interval from 0 up to some given argument. Let's say the parametric maximum from here to here. And the statement says if we can compute this parametric maximum in polynomial time of this function, then the original decision problem, we can actually decide that in polynomial time. How can we decide that? Well, let's calculate the parametric maximum up to here, right, from this interval. And of course, the maximum will be dominated by this pulse if this pulse is present, right? If this pulse is absent, then the maximum will be dominated by some of these pulses if they're present or absent. But the height difference between these two pulses is just barely large enough so that we can distinguish these cases in polynomial time. So here, in this example, there are two possible positions for witnesses, right? And if in any of the two witnesses, or maybe both, are present, then the maximum, parametric maximum up to here will be this value. And if none of the two candidate witnesses is present, then the maximum will be somewhere in this range. But the gap is large enough so that we can uh, evaluate the function up to polynomial precision, now like precision 2 to the minus n cubed or something, to distinguish whether the maximum is this or whether the maximum was smaller or equal to this. And this distinction will tell our algorithm whether there was a pulse present or not, right? Which is exactly the question that the NP problem wants to know for this. Fair enough. Example, toy input n equals 2. Check whether there exists a witness. Well, there are only two possible witnesses, but the point is we can answer that now by looking at the parametric maximum from 0 up to here. And the same, of course, applies also to n equals 3. See whether any of the three candidate witnesses is present is determined by whether the maximum up to here has this value, or if all the three witnesses are absent, the maximum will be something smaller or equal to this height dominated by these pulses, which can be distinguished in polynomial time. So the message says we can distinguish whether there exists a witness, whether exists one of the candidate pulses by distinguishing only approximately within polynomial time up to polynomial error, whether the maximum value is large or small. And since the hypothesis says this can be determined in polynomial time, that means we can recover the question, answer to the question whether n belongs to this NP problem or not, also in polynomial time. And this is exactly the statement. Okay, let's take a short break here because this was really an involved construction over 4 steps. We initially started by encoding a discrete, well, the entire integers into the unit interval with all pulses present. Then we would remove some pulses and thus encode a discrete decision problem. That was our second step. In the third step, we would further subdivide the intervals to allow for candidate witnesses. And in the fourth step, we would encode the entire verifier into these various pulses and assert that the function is polynomial time computable, because at each position we only need to, we're basically given both the input and the witnesses, right? So each position encodes an interval, and interval corresponds to these pairs. But computing the maximum requires to look at all possible candidate pulses, at all possible candidate witnesses. So being able to compute the maximum in polynomial time allows to recover the question whether there exists a witness, and thus allows to decide this problem in polynomial time. And our scaling was very carefully constructed to make sure that the resulting function is still smooth, right? So that required us to kind of apply this dampening, right? So that all derivatives also tend to 0 towards when t tends to 0, but just not too much dampening, so that the resulting function, the separation between the pulses is still large enough so that we can distinguish that separation in polynomial time. Okay, so that was a short version of our involved, well, this, I have to say, yeah, the credit of this construction is given to Harvey Friedman, a famous logician in the States, and his the then PhD student, Carrie Coe, who unfortunately passed away last year. You may have heard about that at the CCA conference. So very involved construction, and it demonstrates or rebukes several folklores in numerics. So smoothness does not help, even in C infinity does not suffice. to guarantee polynomial time computability of the parametric maximum. And observe that we would need the parametric maximum because how long the interval is over which the maximum is to be taken, that is the way to encode the discrete integer input. Also, let me point out that this resulting function has many local maxima, right? So, namely, every pulse constitutes a local maximum. And this is intuitively what makes maximization problem so hard, right? Newton's method is easily able to find the maximum in polynomial time given an appropriate starting point. I mean, when given a starting point here, Newton's method will quickly converge here, which is only a local, well, in this example, it's a local, but here, let's say we start here, then Newton's method will converge here into a local maximum, but this is not a global maximum. So computing global maxima, that's what makes this function hard to maximize. Local maxima are easier, or put differently, finding the right starting point to Newton's iteration. This is a crucial part that is often ignored or neglected or postponed in numerical analysis. Here we would need to have a starting point that is already close to what we later turns out to be the global maximum. And here this will not converge to global maximum. So our different perspective is, let's say we guess a starting point in Newton's method, then and then run Newton's method to verify that there's a maximum at this point. But this guessing part, this is precisely what corresponds to NP, and this is this should be given, I think, more focus in numerical analysis, how to find a good starting point, because this is exactly what makes the problem hard as NP here. The final remark, our analysis here is, of course, shows optimality of our algorithm for computing maxima using this NP decision problem. So we cannot expect anything better. And this is independent of the algorithm use, right? So this is not like analyzing an algorithm and hoping for a different algorithm to be better. But this is, as is common in computer science and complexity theory, this is about the intrinsic complexity of the problem and not about some specific cost of an algorithm. Okay, so that was a long speech about one single slide about one problem that parametric maximization is in a sense NP hard. And now in the remaining time, we're going to similarly investigate the intrinsic computational complexity of the other problems that we have considered so far. So for maximization, NP is kind of optimal. Now, how about integration? Well, for integration, we can basically reuse the same construction as previously. Now, not looking for the existence and the maximum, but counting the number of pulses is an indication, or actually counting the area under the pulses is similar an indication of the number of witnesses, which is precisely the definition of a Sharpe hard problem, right? So let me state again formally, again without reduction, but the statement says to every counting problem in Sharpe, so psi is now not a decision problem, but a counting problem, count the number of witnesses, there exists a polynomial time smooth function, namely this here, such that the parametric integral, the indefinite integral, is polynomial time computable if and only if the original counting problem was actually already solvable in polynomial time. And observe here that the integration here has two integration bounds, but this is not really necessary. We can also consider just integration from 0 up to 1 integration bound, and then integration up to x, again from 0, and then take the difference between both, right? So the integral from x to y is equal to the integral from 0 to y minus the integral from 0 to x. So again, we can only consider only ordinary indefinite integration with only the upper integration bound varying. And let me say it again, the proof idea is instead of checking whether witness is present by checking whether the pulse is present, which affects the maximum of the function, here we can check how many witnesses are present by counting how many pulses of the large pulses are present by because the area under these pulses, that is the integral, is an indication of the number of pulses. Right? We just need to divide the overall integral, the overall area, by the area of one single pulse, which is some fixed polynomial time computable number here, and thus recover the number of pulses present. So that means that also integration or Sharpe algorithm for indefinite integration is optimal because we can in this way encode discrete counting problem into Riemann integration. And if we prohibit, actually the construction here is a little bit more subtle when we consider a definite Riemann integration. I'm not going to explain that in further detail, but the message here is that also definite integration, Riemann integration Sharpe-1 is also optimal in this similar sense. Okay, so that's our second problem. And now we move on to consider, right, that's here, integral. And so now we've characterized actually two famous discrete complexity conjectures from discrete complexity in terms of numerical problems, right? So this is I think this is extremely astonishing, right? So we've characterized the P versus NP problem as the complexity of parametric maximization of one explicit thing, as one maximization of one function. Again, that's very different from the discrete setting where deciding one specific instance is always possible in constant time, right? This is like this this example. It's decidable whether God exists in polynomial time, namely one algorithm that says yes, one algorithm says no, and one of the two algorithms will give the correct answer in constant time. Well, I don't know which one, but you see the point. So similarly in discrete complexity, the complexity of individual instances is always a constant. And what makes the problem hard, NP hard, or even undecidable is having infinitely many instances. Here in the continuous realm, we have one instance, one function that encodes the entire decision problem with its infinitely many instances into one continuous object, and the complexity of determine the parametric maximum of that one single function, or the complexity of determine the indefinite integral over that function. This is what we don't know, the complexity of this single integrated function. Okay, so yes, parametric maximization characterizes the discrete complexity class Sharpe. Indefinite Riemann integration characterizes the discrete counting complexity class Sharpe. Definite Riemann integration characterizes the discrete counting complexity class Sharpe-1 with unary inputs. And they are similar such statements. For example, Akitoshi Kawamura has proven that solving ordinary differential equation is not just feasible in polynomial space, yeah, by Euler's method, but actually that this is optimal. So he proved that this characterizes PSPACE in the similar sense by encoding an arbitrary generic PSPACE problem into the right-hand side in a very sophisticated way. So that question had been open since Carrico posed that in 1991 in his book. So for 20 years, and then Akitoshi Kawamura has given a positive answer to that question. Right, so I'm not going to show his construction, which is really very involved, but maybe sometime you get a chance to listen to a talk of him about that. Moving on to further more complicated problems in numerics, solving partial differential equation, not ordinary, but partial differential equation, which intuitively should be more difficult than ordinary differential equation. But on the other hand, we're here restricting to linear partial differential equation, namely to Poisson's equation, whereas the ordinary differential equation that Akitoshi proved to be PSPACE hard is actually a nonlinear right-hand side. So Poisson's equation, partial differential equation, is this equation. So here you see the Laplace operator, the sum of second spatial derivatives on the left-hand side must equal given inhomogeneity f on the right-hand side, which is supposed to be polynomial time computable. And we have here imposed some boundary condition to make the solution unique, namely the function should vanish at the boundary of the, here let's say unique disks. Let's say we consider this partial differential equation. Every partial differential equation needs a domain, and here the domain we consider is the unit disk, Euclidean unit disk. We can similarly consider also higher dimensional, like the unit ball, but for here, let's just focus on this. And the statement obtained in the PhD thesis of Florian Steinberg is that this partial differential equation also characterizes a discrete complexity class, namely the sharp P complexity class, in a similar way that in a intuitive sense, solving this linear partial differential equation is as hard as indefinite Riemann integration, which maybe have come quite as a surprise. So it's not that hard, but it's also not that easy. And an important part of the statement also is that the solution is a classical one, which I will say more about in the next slide, where we actually establish that statement of Florian Steinberg from his PhD thesis. And another final numerical problem we want to consider in this lecture is the heat equation. So here you see the heat equation. The heat equation is an evolution equation. So here it's a static problem, but here we have a time parameter, and we have a given initial condition on the, let's say, the torus. So this is the unit cube, but with periodic boundary condition. I'll say again more about that later. So, and it turns out that this also characterizes sharp P. So, which is kind of surprising, because it's well known from that the solution theory of this partial differential equation is quite different depending on whether it's a elliptic, parabolic, or hyperbolic partial differential equation. But so far, for these two examples at least, it turns out that the intrinsic complexity is the same as sharp P. Okay, so and yeah, we're currently working on the third example, the wave equation. But anyway, so this is a very new result obtained by Ivan Kosvara, Gleb Bogutin, Svetlana Selivanova, and me. Okay, so let's spend the remaining 15 minutes of today's session by understanding why and in what sense Poisson's equation is Sharpie complete, characterizes Sharpie in the same way that indefinite Riemann integration does. So here's for your convenience again our equation, and now formulated in the d-dimensional Euclidean unit disk. Euclidean is important. So for example, in dimension 2, this is just the ordinary disk. And inside the disk, Laplace U, the solution, use the solution, must be equal to the inhomogeneity driving external drive F, and on the boundary here it should vanish. That's our equation. And yes, this is Laplace operator is an abbreviation of the sum of second partial derivatives, x twice differentiating with respect to x, twice differentiating with respect to y, and so on, depending on how many dimensions we have. And intuitively speaking, the Laplace operator captures the curvature of the function u, right? So first derivative is slope, and second derivative is curvature, that is the reciprocal of the radius of an inscribed or touching circle, right? That's curvature. So that the right-hand side basically prescribes or defines the curvature of this function. Okay, and here you see an example solution. So it's defined on the unit disk, and yeah, it kind of bulges up here. So it's in this example a function defined on the unit disk with values in the z-axis, the three-dimensional, so that you can imagine that. Yes, so Poisson's equation is a partial differential equation, time independent, but already mathematically the solution theory for partial differential equations is pretty subtle and involved. So for example, there's this example due to Levy from 1957, who constructed a partial differential equation which does not have a solution. So the kind of yeah, which is kind of different from ordinary, where already continuity of the right-hand side implies, according to Peano, that there exists a solution, and the uniqueness was the problem where we need stronger smoothness hypothesis. Here already the existence is a subtle question. And let me also remind you that for the Navier-Stokes partial differential equation, existence and smoothness of the solution is one of the famous millennium problems. So we have to be very careful when we deal with partial differential equations, and first make sure that the PDE we're considering actually has a solution, and in what sense a solution. So so one thing one's commonly imposed or required is that the problem be well posed in the sense of Hadamard, which means three things. First, there must exist a solution in a certain function class, right? For example, if we want here the solution u, and the right-hand side is continuous, then we may want the solution will be twice continuously differentiable, because then differentiating twice according to the Laplace operator will be equal to the continuous right-hand side. So in this case, we might consider the set of twice continuously differentiable solutions as a solution space, but it turns out that this is not in general the right class, which I'll say more in a minute. The second condition for well-posedness is that the solution should be unique in that class. So if we make the class too small, then we may not have a solution. If we make the class too large, then there might be several solutions. So finding the right class for a given PDE such that the PDE becomes well-posed is actually a common and important mathematical challenge. Yes, such as for Navier-Stokes. And the third condition is the solution should depend continuously on the data being here, for example, the right-hand side. So if we perturb the right-hand side a little bit, then intuitively also the solution should vary also a little bit. But what does it mean to vary a little bit? That, of course, depends crucially on which function class we're talking about. If we're talking about continuously differentiable functions, then we may use the norm supremum of the first derivative plus supremum of the function, which is a Sobolev space norm, which is already pretty involved. So when I say here just continuously dependence, there's a very subtle questions underlying that to make that formal. Depends on the class of functions and on a topology, or better, a metric, or on that functions space. Right, and regarding Poisson's equation, there's a famous counterexample to Petrini from over 100 years ago, who constructed a continuous right-hand side f such that the solution, that the PDE, Poisson's partial differential equation, has no classical solution, no twice continuously differentiable solution. So as I said, this is something that one might expect or impose naturally for a solution, because taking the second derivative should be equal to the continuous right-hand side. But if we require the solution to be twice continuously differentiable, that would be the requirement for an ordinary differential equation, right? That the solution be as often differentiable, continuously differentiable, as the right-hand side is. But here, this is not the right notion. So already to make the complexity theoretical question relevant, we need to be very careful about which class of right-hand side we consider. And in general, this mathematically seems that weak solutions, weak derivatives with integrable first derivative, that is Sobolev solutions, is the right function space here in general.